Bismillahirrahmanirrahim or Assalamu alaikum. I hope you are all well and taking good care of yourselves given the current situation. Um, the most important thing is your health and safety. So please आप लोग अपना और अपने घर वालों का बहुत अच्छी तरह ख्याल रखें और घर के अंदर ही रहें. So, as you are all aware, we're trying to move to online learning. I hope Ke Abdullah would have shared with you the online learning plan. So, my plan is Ke I'll be sharing with you the PDF slides as I always do, but I'll also make these videos with audio and screen grab of the slides to help aid your understanding essentially. So, I hope Ke this will be useful for you. So basically, if you're listening to me, then you have made it to the YouTube channel, which I've set up for this purpose. तो इसका channel का link हमेशा I'll leave in the PDFs ताकि you can always get here. So let's jump right into where we had left off before our semester was interrupted. So if you recall, basically what we've been doing was that हम एक नई problem, that is beam bending को analyze करना शुरू हुए थे using the finite element method. So up till now what we'd done essentially was that we had looked at a particular beam bending problem और फिर हमने उसके एक infinitesimal element के equilibrium को consider करके उसकी strong form, that is the differential equation governing the beam bending problem को derive किया था. And when we did that, we saw that this differential equation this differential equation governing beam bending actually turned out to be a fourth order differential equation. Okay, so this was new for us because before that we hadn't solved a differential equation with such a high order using the finite element method. So essentially, we saw that initially the procedure for the finite element formulation follows the same method as we are already aware, which essentially involves converting the strong form into the weak form, which I've done right here. और weak form के लिए हम एक weight function से multiply करके integration by parts करते हैं. This time, because it's a fourth order differential equation, we actually do integration by parts twice so that we can shift two orders of the differential onto the weight function. Two orders of differential from our trial function, that is the deflection V of the beam, onto our weight function, arbitrary weight function W. So that now when we've got our weak form, that is at most a second order differential equation. ठीक है जी. So, and then beyond this, we use our Galerkin approximation as before, where we have our W and the deflection V being interpolated using shape functions, basically, right? And then we see that आगे जाके अभी we'll come to the shape functions in a second. Okay, that is where we need to be careful when we have a weak form जो at most जिसमें second order differentials हो, तो उसके ऊपर अभी हम आते हैं. So basically this weak form, once it's been manipulated using the Galerkin approximation, can also be written as our standard finite element problem given by this expression right here, Ka is equals to B, where this is our very familiar K being our global stiffness matrix. A is our nodal vector with the degrees of freedom, and then B finally is the global right hand side vector. Normally, as we've already discussed this before as well, the global K and B are also they're not found directly for the global problem, but instead हम element wise इनको find करके K को और B को, and then we assemble them into the global matrices, right? Okay. So when we do that, so we can write our stiffness matrix and our right hand side vector actually in element wise form. So element wise, my stiffness matrix is given by this expression right here, where this does actually correspond to the weak form if you look carefully. So there's EI right here, and then there's our B matrix, the capital B matrix, contained within it. So we had already gone through this before, so agar if there's any confusion, please do refer to lecture 7, and I'm sure udhar sari clear ho jayega. I'm just going through a little quick summary of everything that we'd covered so far. So as we discussed this time around, um, in order to deal with the fact that our weak form has second order differentials, we need to introduce some new shape functions. So that means कि ये जो हमारा B matrix है, which itself contains, of course, the derivative of the shape functions, these need to be defined in a new way. So this time around for beam bending, we saw that we have to use new type of shape functions referred to as the Hermitian shape functions. These Hermitian shape functions look like so. I'll come to these in just a second. Such that using the Hermitian shape functions, my N matrix, which contains my shape functions, takes this expression right here. And then my B matrix, which contains the derivatives of the N matrix, basically actually contains a double derivative. Why? Because double derivative, because it corresponds to this double derivative corresponding to the fact that we have double derivatives in our weak form. Okay, great. So what are these shape functions? So we had gone through in the class that these Hermitian shape functions, essentially we introduce 2 degrees of freedom per node. And a Hermitian element essentially consists of 2 nodes, node 1 and node 2. But unlike our Lagrangian shape functions, इस दफ़ा हर node के लिए 2 shape functions होते हैं. Each node has one displacement shape function represented by n, and each node also has a rotation shape function represented by m. Now, these have some unique descriptions or definitions which we've discussed previously. Basically, that the displacement shape functions are, as we know before, that they take a value of 1, that they take a value of 1 at their own node. So n1 is 1 at node 1 and 0 elsewhere. But also that their derivative, if you look carefully here, their derivative is 0 at all nodes. So it's 0 right here, and it is indeed also 0 right here if you look carefully. तो इसी डेफिनेशन से जो नोड नंबर 2 का डिस्प्लेसमेंट शेप फंक्शन है वो भी इसी तरह है दैट इट टेक्स अ वैल्यू ऑफ 1 एट नोड 2, 0 at all other nodes, and its derivative is 0 at both nodes. Okay, correspondingly we have our rotation shape functions m1 and m2. Now these rotation shape functions are actually 0 at both nodes, but it has a derivative of 1 at its own node, so that अगर मैं m1 की बात कर रही हूँ, so m1 actually has a gradient of 1 at node 1 and a gradient of 0 at node 2 basically. And similarly for m2, I'm sure you get the picture basically. Okay, so this is how then we find our n1 and our shape functions. From our shape functions, we get our shape function matrix. From our shape function matrix, we get our B matrix, which contains the double derivatives of the shape functions. And once we've got our B matrix, we can find our element-wise stiffness matrix and then assemble it into the global stiffness matrix. इसी तरह राइट हैंड साइड वेक्टर के साथ भी होता है, लेकिन दिस टाइम अराउंड राइट हैंड साइड वेक्टर जो है वो एलिमेंट वाइज डिफाइन होगा द राइट हैंड साइड body vector basically. So I represented with b omega right here. This omega stands for the domain or the body, right? So it's the effect, it contains the effect of the distributed load जो act कर रहा है उसके ऊपर, so पूरी body के ऊपर जो load act कर रहा हो. So B omega then consists of this expression, which has an integral of the shape function matrix essentially, and the distributed transverse load acting on the beam, right? Once we've got our element-wise body vector, we assemble this into the global body vector. That is, we assemble it into the global B omega. And then finally we find our global right hand side vector by also adding together the effect of the point loads which may be acting on the beam. So for example, here I have drawn in there's this transverse force, which is a point load, and there is a point moment being applied right at the end of the beam. And of course, once we remove this wall support, there will be reactions also acting at this point. So there are these two nodes on which there are point loads acting. So these will have to be incorporated using B point, similar to the procedure that we had used for our axial loading problem. Okay, so just to repeat that again, that the global right-hand side vector consists of a body term, the assembled body term, and the point loads, which consists of the effect of a transverse force and a moment being applied at a node. अब इसके अंदर सिर्फ हमें बहुत ध्यान से क्या करना होता है कि जो फोर्स है उसको फोर्स टर्म में ऐड करना होता है इन बी पॉइंट, और जो मोमेंट है उसको मोमेंट टर्म में ऐड करना होता है फॉर बी पॉइंट. वी विल गो थ्रू दिस यूजिंग एन एग्जांपल that we'll just see shortly. Okay. Lastly, the whole purpose of this exercise is to find our trial function, which is our deflection of the beam, that is V, the vertical deflection of the beam. So this V within an element is basically given by an interpolation within it using our respective shape functions and their corresponding degree of freedom. So N1 of course corresponds to V1, which is the deflection of node 1. And then M1, the rotation shape function, corresponds to, of course, the rotation at node 1, so theta 1, right? Again, this can also be represented in a compact matrix notation by using our shape function matrix and our degrees of freedom vector. So degrees of freedom vector के अंदर we basically have our deflection and rotation for each of the nodes, where we just need to be a little careful कि हमें जब again इनकी values जब input कर रहे हो अपने a vector के अंदर, तो हम ध्यान से deflections को deflection की terms में डालें और theta rotations को rotation की terms में डालें. So convention of course follows deflection of the first node, then rotation of the first node, and then deflection of the second node, rotation of the second node, given just for one element. Okay, so this is just a recap of everything we had done so far. So now let's use this whole methodology that we had developed to jump to an actual beam bending example. So we are going to consider this particular problem shown right here, where our left-hand side of the beam is fully fixed, and then right in the midpoint of the beam we have a fixed, no, what is this? Sorry, a roller support, which of course prevents any deflection right here. And then there's a distributed load acting downwards, और फिर उसकी dimensions भी given है. Recall कि हमें also material property or geometric properties of the beam भी चाहिए, which combined together have just been provided to us, that the bending stiffness of the beam, which is this property EI, is equals to this particular value given right here. Okay, so what we're being asked, that we're going to use the FEM method to find the deformation and reactions for the following clamped beam, this clamped beam. And we are going to discretize, the beam is discretized using two equal length, two node Hermitian elements. Okay, that means, let me draw this out. So we are saying two equal Hermitian elements, so that I will have one node right here. This will be my node 1. Oops. And then second node midpoint के ऊपर आ गया. Node, come on, node 2. And then finally node 3 इधर आ गया. Great. Okay, so ये मेरे 3 nodes हो गए, and I have my 2 elements, one element right here and the second element right here. Okay, तो हमने इसको solve करना है. Great. Okay, so let me just write down all the finite element formulation basically for the beam bending problem ताकि हमारे पास वो सामने नज़र आ रही हो आसानी के लिए. So we know that our global problem is represented by this. This is the global finite element equation. Ka is equals to the right hand side vector b, which consists of b omega, the body term, and the point term. Okay. And then within this, the global stiffness matrix is actually assembled from the element-wise stiffness matrices, so that our element-wise stiffness matrix is given by this expression, and my element-wise body, right-hand side body vector is given by this expression right here. Do we need anything else? Yes, I think we need to know what NE and BE are. So NE, of course, is the shape function matrix, and B is the B matrix, which contains the derivatives of my shape functions. Okay, all of this. Now, what is N1, M1, and 2? They are all our standard Hermitian shape functions, which we now recall they look like this when drawn out. बट उनकी एक्सप्रेशंस जो हैं जो हमें अगर एक एलिमेंट के अंदर उसकी अरिथमेटिक एक्सप्रेशन फाइंड करनी हो दैट्स गिवन बाय दीज एक्सप्रेशंस राइट हियर. Of course, you do not need to memorize these. You can look this up in any textbook you want, and you will be provided these whenever you do need to use them. Okay, all these expressions for N1, M1, N2, M2. Okay, so let's start. So first of all, we are going to discretize our beam using our two elements. ठीक है जी. और उससे क्या होता है? Of course, we will find our stiffness matrix and our right hand side body term for each element first and then assemble them. So पहले तो मुझे discretization से start करने दें. So I have my two elements, right? I've got my element 1 and my element 2. So element 1 has nodes at x is equals to 0 and x is equals to 5, and then element 2 का एक node हो गया ये x2, and then finally the third node at the end of the beam at x is equals to 10. Now recall that for our Hermitian shape functions we have 2 degrees of freedom per node. So I have to give these degrees of freedom some names. So what I'm going to do is I'm going to say this node has global degrees of freedom 1 and 2. Node 2 has 3 and 4. And then finally this one has global degrees of freedom 5 and 6. And then I'm going to start to consider them locally. That is, just look at them within each of the elements. So let me first look at element 1. अब element 1 के लिए I just have my local node 1, local node 2, and their local degrees of freedom are then 1, 2, 3, 4. Okay. और element 2 के लिए भी similarly मैं local degree of freedom numbering same use करूँगी. So this is my local node 1, local node 2, local degree of freedom 1, 2, local degree of freedom 3, 4. Okay, great. Now we recall that once we've got our local and global names for our degrees of freedom, then we can use our local to global degree of freedom map to figure out how the element-wise matrices would assemble into the global stiffness matrix. So let's jump into this. सबसे पहले I think हमारे लिए आसान होगा कि ज़रा इन सब के size लिखना शुरू कर दें. So अगर मैं अपने individual elements को देखूं, then I can see that I have a total of 4 degrees of freedom in element 1 and 4 degrees of freedom in element 2, एक Hermitian element के. So if I have 4 degrees of freedom, then the element stiffness matrix is going to have a rank of 4 by 4, whereas its right hand side vector, the element wise right hand side vector, will have a rank of 4 by 1. ठीक. Similarly, ये element 2 के लिए भी this holds true, right? So each element has these ranks, right? What about the global one? So globally, I have how many degrees of freedom? 1, 2, 3, 4, 5, 6. So that means that my global stiffness matrix, capital K, will have a rank of 6 by 6, sorry, I did not write it down, but this is basically, let's check, 1 2 3 4 5 6, 1 2 3 4 5 6. Global k would be then 6 by 6, और the global right hand side vector जो है, अभी first उसकी सिर्फ body term लिखी गई है, will then be 6 by 1. ग्रेट. तो हमें उन दोनों के जब सबके रैंक्स पता चल गए, देन वी कैन जंप टू, पहले जनरली अगर लिखना चाहें तो वी कैन राइट देम आउट. सो एलिमेंट वाइज स्टिफनेस मैट्रिक्स वुड बी समथिंग लाइक दिस, 4 by 4 मैट्रिक्स, और द बॉडी वेक्टर वुड बी समथिंग लाइक दिस, 4 by 1. और ग्लोबल जो है उसको हमें फिगर आउट करने के लिए, एक सेकेंड, आई विल हैव टू मूव बैक बिकॉज वी नीड आवर local to global degree of freedom map to figure out how the element wise assembles into the global. So uske liye let's see our degree of freedom map. So for element 1 I have local degree of freedoms 1 2 3 4, and I can see ye 1 2 3 4 जो है ये global से भी 1 2 3 4 से ही map कर रहा है. So 1 2 3 4 right here. Whereas for element 2, local I have 1 2 3 4 being mapped to global 3 4 5 6. So 3 4 5 6. Great. Then हमने assembly का procedure तो अच्छी तरह आप देख चुके हैं. So what I do is I first will write down my empty global stiffness matrix with a rank of 6 by 6, and then I'll start to fill it up. So for example जो मेरी global 1 by 1 की position है, I only have a local mapping, local of element 1 की 1 by 1 वाली that goes in there. So and then I can fill up basically all of these terms. But basically I just by looking at this problem I can see that it's only these, the global degree of freedom 3 and 4 जिसके ऊपर वो दोनों elements contribute कर रहे हैं. So only for the global degree of freedom 3 और 4 वाली जो सारी terms हैं, these ones right here. So 3 3 3 4 4 3 and 4 4, उसके ऊपर दोनों एलिमेंट्स की कोई कंट्रीब्यूशन होनी है. और वो कंट्रीब्यूशन क्या है? इफ़ आई लुक एट माय ग्लोबल वन, 3 3 से एक तो मेरे पास आ रहा है, probably change my color. Okay, 3 3 के ऊपर I have 3 3 from element 1, so 3 3 from element 1. 4 4 के ऊपर I have 4 4 from element 1, so 4 4 from element 1. Then 3 4 के ऊपर मेरे पास है 3 4 from element 1, 3 4 from element 1, and finally 4 3 के ऊपर I'll have 4 3 from element 1. तो ये सारी terms आ गई, right? ये वाली and ये वाली from element 1. Whereas if I now look at the degree of freedom map for element 2, I see कि मेरे global 3 3 के ऊपर element 2 का 1 1 भी है. That is, I have 3 3 global वाले के ऊपर 1 1 आ रहा है element 2 का, ये वाली term right here. And then exactly same procedure से 4 4 पे I know there is a 2 2 coming up, and then 3 4 के ऊपर 1 2 और 4 3 के ऊपर 2 1 finally. So yeah, I think कि आप लोगों को assembly तो पूरी तरह याद है. इसी तरह हमने अपने body vector को भी या फिर domain vector को भी which contains the effect of the distributed load, उसको भी इसी तरह assemble करना है using the local to global degree of freedom map, noting again कि it's only the 3 4 degree of freedom जिस पे वो दोनों elements contribute कर रहे हैं. So 3 4 के ऊपर I end up getting local degree of freedom 3 from element 1 and local degree of freedom 4 from element 1. So this term right here, these two terms right here, and from element 2 I get B1, degree of freedom 1 and degree of freedom 2 right in there. Okay, तो हमने अपनी assembly को भी general expression के तौर पे लिख लिया है. But now what we need to do is actually to find के ये KE, ये what are these KEs for my individual element 1 and element 2, and what are my body vectors for my element 1 and element 2. Okay, so we'll jump to this. Let me just see what the time is. I think I'll upload these in 20-minute intervals ताकि थोड़ी short हो. So I'll just jump to part 2 immediately after this in just a second.